Okay, so we are in the second edition of Statistical Rethinking. We're in Chapter 9 in the easy questions, and we're on question 9E4. So here's the question. So explain the difference between the effective number of samples, or N sub EFF for effective, as calculated by Stan, and the actual number of samples. Okay, so let's start by describing what NEFF is. And also, it's not really clear by the actual number of samples. Could be a little bit of an ambiguous term here, so I want to clarify all of this. Okay, so as a first pass here, when we run our sampling algorithm, like MC, we run it for some number of iterations, say 1,000 iterations or whatever. And those iterations, each one of those iterations is providing one sample. Okay, so I believe that the actual number of samples refers to the number of iterations. Okay, all right. So then why not just take the number of iterations as being the number of samples? Okay, and the reason is because the number of iterations, well, each iteration is related to the other iterations in the run, right? And that's just a byproduct of how the algorithm has to work. Okay, so why is this important? Okay, well, if we're going to go out into the world, we're not simulating, but we're going to go out into the world and try to collect information on, say, the average height of a population, right? Well, we want independent samples, right? We don't necessarily need independent samples, and we'll talk about why here, but independent samples give the maximum amount of information, inform our estimate maximally, because the samples are not related. If the samples are related, say that we take the height of a family or something and then use that as our sample for a population, well, that's not going to be very good because that family is related, and so their heights are going to be related. And so the amount of information that family provides is going to be less than the same number of independent individuals that are not related, right? So just to kind of bluntly answer the question, the difference is that the actual number of samples provides less information than independent samples. And the number of effective samples is our estimate of the number of independent samples it would take to produce the same amount of information that was contained within our dependent samples. So that answers the question. But I thought it might be a little bit interesting to learn a little bit more about NEFF, about number of effective samples. Okay, so let's do that. So let's say that we're trying to estimate any parameter, generically called theta, but we'll try to estimate the mean of something. Okay, and so we're going to estimate mu. So theta equals mu here. So our estimate of mu is we'll call it mu hat. Okay, that's our estimate of mu. Okay. And we could get an estimate of mu, again, mu hat, by taking many, many samples and then taking the average of those samples, right? So each sample is an estimate of mu, okay? And it's just when we take the average of those different samples do we get our estimate of mu, okay? So the formula for that might be the sum of all of our samples, which I'm representing here with mu tilde, okay? And then we divide by the number of samples we took. All right, so that would be our estimate. So then mu hat would be distributed as a normal distribution centered with a mean of mu, the actual value, and a standard deviation of this thing, the standard, which we refer to as the standard error of mu, or the standard error of the mean, okay? Where the standard error of the mean is given by this expression, which is our estimate of the standard deviation divided by the square root of independent samples, which I'm denoting by capital N. Okay? So in other words, as n gets bigger, the standard error gets smaller and our estimate of mu hat converges to mu. Okay, so we could also say then that our estimate converges to the actual value of a parameter, okay, like 1 over the square root of n. Okay, right? So as n gets bigger and bigger and bigger, mu gets closer, or mu hat gets closer and closer and closer to mu. We could also say that as n gets bigger and bigger and bigger, SE converges to 0. It approaches 0. Okay. So just to give a sense of what this might look like graphically, so I have an estimate for sigma hat. Okay. 1. Or I should say I have an estimate for sigma, which is called sigma hat, and it's 1. And then I have a series of samples, 1 through 1,000. Okay. And then I'm estimating the standard error for each one of these sample sizes, which again is just sigma hat divided by the square root of the sample size. Okay. And so I'm just plotting it, and so this is what that would look like, right? So this is standard error, and again, you notice that as n gets larger and larger and larger, standard error gets smaller and smaller and smaller, asymptotically approaching 0. Okay. All right. So what's important in all of this stuff is that this is all assuming that we have independent samples, right? We have up to 1,000 independent samples. Okay? But again, that's not how our MC sampler is working, right? We have dependent samples, and so we need to account for that dependent structure among samples. Okay. So we can think of the number of effective samples as being an estimate of the number of independent samples we would need to get the standard error that we obtain with our dependent samples. Okay, so that's a mouthful, but it's written here in the Colab sheet, so hopefully I've said it clearly enough here that you can kind of parse that sentence for yourself and get comfortable with it. Okay, so so I want to show the expression, or an expression, for the number of effective samples, and this is it. Okay, so again, notice that the number of effective samples is an approximation of independent samples. Okay, and the derivation of this is kind of technical. You need to understand how to manipulate variances and covariances, but the derivation is not really important, so I'm not showing it here. What's more important is that we grok the intuition here. All right, and I think that if you just operated on the premise of intuition, you could almost come up with exactly this equation right here. So without any derivation, so let's go through what this expression is saying. Okay, and the intuition behind it. So we know that if n is the number of samples generated by our sampler, we know that the number of effective samples is going to be less than that. Okay, it's going to be less than the number generated by our sampler. Okay. So how much less? Well, the more correlated the iterations are, then the greater the difference is going to be between number of effective samples and the samples produced by our sampler. Okay, so that correlation structure is being captured or summarized down here. All right, so here we have rho hat sub L, and rho hat represents correlation between one iteration and another iteration L iterations away, where L stands for lag, right? So if L equals 1, then this would be like the correlation. This would be like the correlation where your data set is iteration 1, iteration 2, iteration 2, iteration 3, iteration 3, iteration 4. Now, if L equals 2, then you would be estimating that particular correlation with iteration 1, iteration 3, iteration 2, iteration 4, and so on. Okay. All right. So anyway, all of the correlation then among samples can be captured by summing over all of these different correlations, okay, from 1 to capital L, where capital L has to be less than the number of samples in your MC run, right? Because you can't have more lags than you have samples. Okay, so so we see then that we're reducing the size of n as the correlations increase among samples. Okay, and that's really the intuition here. All right. Now this 1 and this 2 sneak in there for some reasons that fall out of the derivation. But basically, notice that that the lags start at 1, so iteration 1, iteration 2, iteration 2, iteration 3. But each iteration is also correlated with itself, which would be lag of 0, and that is 1. Okay, so rather than putting it here, starting at 0, we put it over here. Why do we put it over here? Well, that has to do with this 2 here. Okay, so all correlations, they're bidirectional or they're symmetric. So iteration 1 correlated with iteration 2 is the same thing as iteration 2 correlated with iteration 1, and both of those contribute to our estimate of the effective number of samples, right? And so we get one of these guys, and we multiply it by 2, right? Yeah, that's a good enough explanation. It really has to do with that this row is actually an autocorrelation function, and anyway, that's reasonable enough. Okay, so now notice, so let's just run a quick sanity check here. Notice that if there is no correlation among iterations, then this term drops out. So all of that becomes 0, and now we have n divided by 1, which is n, in which case the number of effective sample sizes would equal the number of iterations, which would equal n, capital N, the number of independent samples, right? Okay, again, if there is no correlation, then the number of effective sample sizes will equal the number of independent samples. Okay, so so let me go through a little bit of a simulation here. Let me actually just hide this output so we can walk through the code without distraction. Okay, so I'm going to have different sample sizes, 1 to 100. Okay, and then I'm going to have different values for the sum of the autocorrelation function down here. Okay, so this guy right here. Okay, so I'm going to have no correlation among samples. I'm going to have 10%, 20. Well, I shouldn't say percent, but correlation of 0.1, 0.25, and 0.5. Okay, and then I'm calculating the number of effective sample sizes for each of those rows, or sum of rows here. Okay, and then I'm going to plot the number of effective sample sizes. Okay, and I'm also going to plot the standard error of those different correlations. Okay, so let me run that. Okay, so this first plot again is the number of effective sample sizes. So the first line, this black line here, again, that represents independent samples. That is when there is no correlation among iterations. Okay, and now you see, and then on the so y-axis is number of effective samples, and the x-axis is n, which again is the number of iterations in our MCMC sampling run. Okay, so when there is no autocorrelation, right, we see that that number of effective sample sizes equals the number of iterations, which means that we have completely independent samples. Okay. Now, as the correlation increases, right, from 0.1 to 0.5, we see that as we get more and more iterations, we achieve smaller and smaller, right, smaller and smaller number of effective sample sizes. Okay, just as well as we predicted. Okay, and now similarly with the standard error here, again, so again, the standard error is showing how quickly our estimate converges to the true value, right? And the best we can do is independent samples, and that's given by the black line, which we already saw up here, okay? But the best we can do is that black line, and as the correlation among samples increases, right, we get slower and slower convergence of the standard error to zero, or another way to say that is we get slower and slower convergence of our estimated parameter value to the actual parameter value. Okay, so I guess that's it. This was longer than I hoped, but I'll see you next time.